Good afternoon, everybody. Thank you very much for showing up in good numbers for this session. My name is Kamran Naqvi, as our friend already introduced. This presentation, my focus will be, you will hear me talking a lot about AI, but a lot of the discussion point that I have, they are also applicable to HPC. So just to save time, I won't be saying AI and HPC every time, but most of this will be relevant to both AI and HPC environments. I will start my discussion by arguing that AI is a distributed compute problem. Would you agree with me? AI is a distributed compute problem because you need multiple computers to run this application, right? So whenever you have multiple computers running single application, because the application is so large, you cannot run it on a single GPU or a single CPU. That is a distributed compute problem. In AI, we are not talking about a couple of CPUs or GPUs. We are talking about dozens, hundreds, sometimes thousands of these GPU running a single application. AI is a distributed compute problem. Now, in a distributed compute problem, network becomes very important. Why? Because all of these different GPUs need to work together and act like a single computer. And they can only do that if there is a very efficient network. So from that point of view, networking plays a key role in any distributed compute problem, whether it is AI or HPC. And I would argue that network is the computer. And by the way, these are not my words, these are the words from Sun Microsystem 20 years ago. Still very true when we talk about distributed compute problems. Now, we have solved distributed compute problems in the past. For example, Google search is also a distributed compute problem, and we know it works very well. So we know how to solve distributed compute problem, but when you look at this slide, it tells a different story. Because this is a slide from Meta. Few years back, Alexis presented this slide where essentially Meta is saying that network is the bottleneck in my recommendation workloads. What they're showing is the time spent or wasted in networking. And if you see, there are 4 different models. If you average out, you will see that on average 35% of the time, these GPUs were waiting for network to complete its job. 1/3 of the time is wasted. Why that is the case? I mean, I said we know how to solve distributed compute problem. Do we not know how to build networks? The answer is that the networking requirements for AI workloads are very different from your standard cloud computing. Now, what are those requirements? I'm gonna talk about 3 specific points here. Why this GPU to GPU communication has different requirements. Point number 1, when we talk about this GPU to GPU communication, we have lot less number of flows compared to cloud computing. Look at cloud computing, you have hundreds, thousands of flows, and they are short-lived flows. In case of AI, there are less number of flows and they are long-lived flows. Look at the training jobs, they are running for weeks, right? Now, what is the problem for a network engineer when there are less number of flows? Answer is, you do not have enough entropy. You do not have enough variety. How does our standard networking work? We look at different flows and we see, okay, this is yellow flow, this is blue flow, this is green flow, and send them on different lanes of the motorway. If you have 4-lane motorway, you are utilizing all of the 4 lanes by looking at the color of the traffic, by looking at the flows, right? TCP port numbers, UDP port numbers. In this case, we see all of these flows as same. There are less number of flows. So obviously, if there are less number of flows, there is less entropy. What happens is, we see congestion. We are not able to load balance this traffic very properly. Everybody agree with me on that? Okay, second problem. This is RDMA traffic. We are talking about rocky traffic. So your entropy, your session definitions are hidden in a PTH header. You look at your UDP header, you look at your IP header, it looks the same flow. And if your switch is looking at the same flow, it will only be matching it to the same link. What happens is you have bandwidth in your network, you have 4-lane motorway, you are only using 1 lane of the motorway. Of course you will have congestion, of course you will have the problems that Meta was reporting. So what we learn is that if we apply our traditional networking model on AI workloads, networking becomes a bottleneck very quickly. And the last point, there is tail latency. These are cyclic flows. So in an AI environment with the machine learning algorithm, the last flow dictates when the cycle completes, and then everybody starts on the next cycle. What it means is a single slow flow slows down everybody, and that is a killer for your job completion time. Now, when we look at the networking level, sorry, I'm rushing through because this is a 1-hour presentation. I'm trying to compress it in 20 minutes, right? If you want more details, you're welcome to visit me at Broadcom booth number 18, and we can talk about it in detail. And at the end, I want to talk about something very important. I want to save some time for it. That is Ultra Ethernet Consortium. How many of you have heard about it? UEC. A few of you, right? UEC specifications finally are coming out today. It's a 565-page document. Very interesting. People have been working on it for 3 years. It is live today. So I'm going to save some time for that. So I might skip a couple of slides. All right. Now, at a network layer, what is causing this problem? The answer is there are 3 points. One is transient oversubscription. By the way, they all apply to HPC applications as well. Transient oversubscription, flow collisions, link failure, and incast. Now, transient oversubscription is not a big problem in AI because we don't make oversubscribed networks. But if you do, there are technologies available. The solution for that is in-network telemetry. We at Broadcom have some very good in-network telemetry features which can be used to tell your source when to throttle up and when to slow down, and that will solve your problem of oversubscription. This flow collision is a big problem for AI applications. And there are 2 ways we suggest you can solve it. We have 2 different architectures which have 2 different approaches to solve the same problem. Approach number 1 is packet spraying. That is simple enough. What you do is, when you receive a flow, you spray the packets across all the available links. You will get very good load balancing, right? You're setting, even for a single flow, you are utilizing all the links. Of course, you will have good load balancing. What is the catch? What is the problem? On the receiver side, now some packets may arrive out of order. So it means you need to have some capability either on your destination leaf or your NIC to reorder the packets. Second approach is what we call cognitive routing, where you have a load-aware ECMP, right? Where you not only look at the links, you look at the qualitative metrics of the link, and you see, okay, if this link is loaded heavily, I will not use it. Although my ECMP hash says go there, I will use a different link. And for the failover, we believe that the failover should happen at a hardware level. That is why we call it zero impact failover. It's a marketing word. I mean, there is no impact, zero impact failure. But when you fail over in hardware, and I will show you in Broadcom Silicon, we can recover within nanoseconds, and I'll show you in a minute. Okay, and finally, in-cache problem can be solved by having a receiver-based credit control mechanism, where receiver tells you, you want to talk to me, I'll give you 20 credits. You want to talk to me, I'll give you 10 credits, and so on. Because I know my capacity. Based on that, I allow senders how much traffic you can send me, and that is why there won't be any in-cache. By the way, UEC has also adopted this. Broadcom has had it in our solution for many years. Now it is a UEC standard. These are the 2 solutions that Broadcom offer for AI networking. The switch scheduled fabric is based on Broadcom's Jericho 3 AI solution. This type of solution, you can buy it from our partners like Arista, like Nokia, and actually many white box manufacturers. In switch schedule fabric, all the congestion control, all flow control, all load balancing, everything is taken care of by the switches. You can use any server, you can use any NIC, any GPU. It's plug and play. In the endpoint schedule fabric, this is based on Broadcom's Tomahawk 5 line of silicon. In this case, your endpoint will also participate in congestion management. So you will using ECN, for example, from your endpoint, right? You can run DCN if that is supported. And leaf and spine, of course, they play an important part in the congestion management. This type of fabric, you can buy these solutions from Arista, Juniper, Nokia, Dell, and I think there are over a dozen vendors who will provide you this solution. We at Broadcom, we do not sell to end customers. We are a technology company, and we have our partners who sell the systems. All right. Which takes me to my favorite topic of the day. And that is, we're very happy to announce that from 3rd of June, last week, Broadcom has started shipping Tomahawk 6. Tomahawk 6 is the world's first 100 terabit silicon. It's 102.4 terabit silicon. It is double the bandwidth of any other Ethernet silicon available in the market, right? Once again, with Tomahawk 6, we keep our track record of being the number one to the market and being a generation ahead of everyone else. I don't have a lot of time to talk about it in detail, so I'll just give you the highlights, right? There are details about every point. There is a feature called cognitive routing. I'll touch upon it a little bit. This is a 3 nanometer technology. Tomahawk 6, how many of you were present in my yesterday's talk? There are a few. If you remember, I was asked this question. I made this statement. It's a marketing word. I like it. I just used it. The sentence was, Tomahawk 6 is not an upgrade, it's a breakthrough. And rightly so, when they asked the question, they challenged me. They said, it's double the bandwidth. You've been doing it for the last 12 years. Why this is a breakthrough, right? It was a good question. But the answer is also not bad. So hear it out. This is a silicon where you can, you can use for both scale-up networking and scale-out networking. So far, what people use for scale-up, for example, any ideas? NVLink, right? Infinity Fabric, and so on, right? With Tomahawk 6 as a scale-up, you can build a scale-up domain of 512 GPUs. I repeat, you can build a scale-up fabric of 512 GPUs. That is 7 times the scale of any other fabric. And I will talk about scale-out on the next slide, right? So, and it's got some industry-leading SerDes and CPO. How many of you have heard about co-packaged optics? A few of you, right? So co-packaged optics is the technology where your silicon has all the silicon photonics. You do not need any pluggable optics. All the optical capability is built into the silicon. So your switches look really, really nice, right? You save a lot of power because it's all built into the silicon, and it's much cheaper. We have a switch based on Tomahawk 5 previous generation family with CPO available at our booth. So do visit us if you have time, and you will be able to see it. This will be the 3rd generation of CPO that we will be shipping with Tomahawk 6. We've been doing it for many years now. Now, scale-out fabric, how much time I have? Okay, so the scale-out fabric, you can build a 100,000 GPU cluster in just 2 tiers with Tomahawk 6. With any other product available in the market, including our own Tomahawk 5, if you want to build this 100,000 GPU cluster, you will at least need 3 tiers, not 2 tiers. Now, what is the benefit of building it in 2 tiers? You use 67% less optics with 2 tier. You will use 67% more optics on 3 tier. You will have more latency, 5 hops. You will use at least 3 times the number of switches, you know. So there are a lot of benefits of getting to the next generation of the silicon, and you will see all the competitors will eventually reach there as well. Broadcom, once again, is the number one to get to 100 terabit per second. I don't have a lot of time to talk about this, but just one feature. Global load balancing. So remember I said load balancing is a big issue in AI networks because of the lack of entropy. With global load balancing, it is like your car's navigation system. When you leave your home for your work, your car navigation system will tell you at the starting point, do not take that motorway, which is maybe 5 miles away, but it knows that there is congestion. Your navigation system says, go somewhere else, take another route. We are bringing that, we have brought that capability into network. With global load balancing, Broadcom Silicon knows the whole topology picture and will guide you to the right link from the first hop. Thor 2 is Broadcom's NIC. It's a 400 gig NIC. This is the lowest power, industry's lowest power taking NIC. It provides you highest RDMA performance. In terms of power saving, at least 40% power saving with our nearest competitor or better. We have George, my colleague here. You want to show your hands? If you have any questions about NIC, talk to George. He specially flew here from America on my request. Please come and ask some questions because you will be asking a lot of questions, yeah? So, George is available on the booth and he can talk about Thor 2. I'm not going to go in a lot of competitive slides today, just one data point from a customer who did the benchmarking. Many of you have already seen this slide. When we compare Ethernet and InfiniBand for training cluster, we see Ethernet outperforms InfiniBand every day of the week. At least 10% better performance in terms of job completion time. Multiple benchmark has been done and proof is in the pudding. And that is why I said that yesterday as well. 7 out of the 8 mega scalers use Ethernet for their AI networking and not InfiniBand. There is a reason for that. They had enough resources, they did the benchmarking, they know what is the right technology for AI. That is definitely Ethernet. And many large networks have been built on Ethernet already. But the idea is that we want to take Ethernet to a level where we can support 1 million GPU cluster. We don't know who's going to build it, but we know that there are people who are already talking about 500,000 GPU cluster. But we want Ethernet to be ready for the time. And for that, Broadcom and 9 other companies gathered together and we form Ultra Ethernet Consortium. We're one of the pioneers. UEC has been working for the last nearly 3 years now. And the output of all this work will be a specification which is coming out today. And as I said, UEC 1.0 specification will be out today. It's a 565-page document. Difficult for me to explain it in the next 3-4 minutes, but I'll just give you highlights. Good thing, at the Ethernet level, UEC, Ultra Ethernet and Ethernet are same. There is no change, right? There is just 1 or 2 optional feature available that you need to do. But the major changes are at the transport layer. You must be thinking, why UEC will be able to scale Ethernet to a 1 million cluster? What is the change? Main change is about modernizing RDMA. RDMA is an old technology. It's a good technology, but it is not suitable for today's large-scale networks. 3 minutes, okay. So I'll just give you a few data points here. RDMA enforces in-order packet delivery. With UEC, what we say is you can do out-of-order placement. What it means is with UEC, you can do a packet spray. Packets arrive at the destination NIC. They are out of order. Even then, NIC will say, okay, this is packet number 1, packet number 2, packet 3 is missing, and packet 4 arrived. Your NIC will put their packet number 4, and after an offset, leaving an offset for 3, it will place it in the memory. And then it can do selective acknowledgement. That is new. You do not have it in RDMA. UEC says that now the receiver will do a selective acknowledgement and says, send me packet number 3 which is missing. Source will only send packet number 3. It will put packet number 3 in order, and now it will send the full message in order to the memory. So this is the in-order message delivery and selective packet retransmission. We definitely UEC allow multipathing. The standard DCQ-CN quality of service is quite difficult, complicated. We build congestion management within the Ultra Ethernet Consortium, within the UEC specifications. So do look out for ultraethernet.org and you will be able to see the specification, or visit us at Broadcom booth. I'll leave you with this final line. We cannot imagine a world where there are millions of these GPUs deployed and everything from GPU to networking is done by a single company. It has never happened in the history of human being. You always have multiple products, multiple vendors. So you need a fabric which can connect all of them. You need a fabric which is open, which is ubiquitous. And we at Broadcom believe Ethernet was that fabric for internet age. Internet will remain that fabric for the AI age as well. Thank you very much.
Thanks a lot, Mr. Naqvi. If you want to have further talk with Mr. Naqvi, the booth is the number D19. So feel free to go there and to lead further talk also with Mr. George Webb.